Opcode 9C, SHY, absolute X indexed. So this is one of the more complex undocumented codes, and fortunately this one and the rest of the opcodes I'm going to talk about have very similar properties in their I guess strange behavior. And so this is one of those instructions that actually takes the high displacement of the address from the instruction, and it uses it as a way to do, well, it's part of the calculation that he uses to compute the final result for the instruction. And this one basically is supposed to take this value, add it with 1, and then AND it with the Y register, and send that to that's the right value. So this value plus 1, AND it with X register, Y register, and then that's gonna appear here. So let's see what happens. So this value is basically 1 less than what is going to appear here. So for example, this is all 0, well, we've got 1 there. So actually if we set this to FF, this is completely zeroed because it's an AND operation. So now the value that allows us to test the Y operand is FE, because FE plus 1 equals FF. So we go to the Y operand, and we also see that, yes, it affects it the same way. So we know that Y value in the high register, this plus 1 is ANDed with the Y value to get this. But here's something that I found out that no one else has talked about yet. Watch the high address when I change the Y value. Notice how it changes. It doesn't change here, it only changes here. And it equals this. So this is where I'm going to explain a little bit of a theory I have on how this this instruction works, or maybe all of the instructions that use absolute indexing to calculate the page boundary crossing address. It looks like what the 6502 does is it computes the high address plus 1 whether it needs it or not, and whether it needs it is based on whether there was a carry generated from the previous ALU operation, which was, you know, adding the low displacement to the either an X or Y register. So I guess that's how the SHY and SHX instructions work. But here's the thing. We get the Y value on the bus here, on the high address bus. Well, that's impossible. Like, there's no instructions that let you do that kind of thing on the 6502. Well, here's one of them, and nobody has mentioned this. But here's the condition. The reason why this value goes here is actually because we're crossing a page boundary. Now, if we take, because this is an X indexed mode, say for example we've got 1 in the X index register, and we've got FF for the load displacement, that causes a page boundary to be crossed, because 1 plus FF equals 100. And that's why we're seeing the Y value on the high address bus. Well, watch what happens when we make it 0. Now, the low address is FF because there's nothing to add. Let's change Y value. Notice that there's no change. So basically, what hasn't been talked about, what I haven't seen on the internet or any other guides or wikis, is that when the addressing mode crosses a page boundary or causes a page boundary to be crossed, it won't happen on this instruction, or I mean it won't happen on this clock cycle, but it will happen on the second one when it actually does the write. So in that case, when there's no page boundary crossing, it's just using the high displacement addresses it would normally use. But so there's also another version of this opcode called, it's 9E, which is SHX, 9E. So that one behaves basically identically to this one, except that it's using the Y index register for addressing, and it's using the X index register for the data calculation, and also what you would see on the high address bus when the page boundaries crossed during the effective address calculation.